It's been hectic, which is always a sign of a really good trip. I've really enjoyed myself so far. So thanks so much for signing up for all the time with me. So I'm going to talk about DESI. I'm going to give a background, but I'm going to really try to drill down on our first year results. We released these in mid-March last year. It came as a surprise, the way the measurements played out, especially when it come out of their probes. I'll try to kind of highlight what the surprises are, but also where some of the confusion lies in interpreting the results. There's some ambiguity. Okay, so I'll try to focus on that primarily, but I got to start with the background. So boring background, but key background is that our project is funded by the Department of Energy, and we have a lot of collaborators. There's about 1,000 people in DESI, so I'm speaking on their behalf, and they're spread all over the world, something like 72 participating institutions. Now, let's start with the cosmology. I'm going to start super general. You've all seen the pie. This is pi. What we want to do is build a survey using this technique called baryon acoustic oscillations. We measure this feature with spectroscopic surveys, primarily with the goal of getting at the cosmic expansion history. So it gives us a standard ruler from which we can make measurements of the Hubble matter to supernova. From this, we can get derived measurements of the Hubble parameter as a function of redshift, and DM, which is the angular diameter distance, as a function of redshift. So these two come out of BAO. We'll talk about the other thing in a second. And the reason we built this experiment was kind of this 20-year saga of trying to understand the nature of dark energy, whether it's Einstein's cosmological constant or something different. And this is good. The discovery of the supernova, from supernova, the universe is accelerating in its expansion, and we want to get at the more detail of that expansion. Okay. There's also other good stuff like neutrino mass. I'll talk a little bit about laws of gravity and inflation, but not so much today. Okay. And the whole idea is I measure large scale structure, I measure that in 3 dimensions with spectroscopy, and I get cosmology out. Okay. So the primary technique we use is called BAO, or baryon acoustic oscillations. This is an artist's rendition of the BAO feature in the distribution of galaxies. So what this is an excess probability. If I have a galaxy, I have an excess probability of finding a pair to that galaxy at a separation of about 150 megaparsec. That's the residual from the CMB. It's the same physics that leads to the wiggles in the CMB. The signal is not as strong as you see in this image, but this is a pretty accurate perspective in that I'm looking from the telescope. I can see this feature in 2 different dimensions. I can see along the line of sight, and there I can measure the feature subtended over a different distance in redshift. So that gives me a direct measurement of h of z, the Hubble parameter. And perpendicular line of sight, this gives me an angular diameter distance. And I can make these measurements because this ruler has a known length and co-moving coordinates. Okay? If I can make this measurement at many, many redshifts, I can get a Hubble diagram, just like I do with supernova.
What's the H and the M for on that?
This is the distance, the Hubble distance, so stick a TH. So this basically goes with 1 over h of z.
Yeah.
And DM is co-moving angular diameter distance. So it's dA, but it's in co-moving coordinates. Okay, so it's times, it's divided by 1 plus z. Gotcha. Okay. So a little bit more about the physics. What is the origin of this BAO feature? It comes from the end of the inflationary period, where when inflation ends, the matter distribution propagates its information throughout at nearly the speed of light. So you get these sound waves traveling out at square root of c divided by square root of 3. And they travel as long as the universe is able to carry a sound wave. So that's as long as the universe is ionized before the CMB forms, basically. Okay, they travel about 150 megaparsec in co-moving coordinates. The CMB, the photons decouple from the baryons, and this matter overdensity in the baryon fluid is preserved for the rest of time. Okay, it has to sync up with the dark matter, but for all intents and purposes, that excess probability of finding baryonic structure is preserved. Okay. Of course, it's not as simple as I showed in the last slide, or is shown here. It's the sound waves are superposition of all over densities in the universe. So you actually have everything superimposed. It's a much more complicated pattern like this. I measure this, I disentangle it probabilistically by counting up pairs of galaxies. And I compute the probability of finding a pair relative to random. And that excess probability is what I show here on the y-axis. So anything above 0 means I'm more likely to find a pair of that separation than random. And you can see this distinct feature at 100 megaparsec. That's actually 100 megaparsec on H, which is why I keep saying 150. And galaxies and matter and gas, they all follow this distribution, okay? So this gives me a standard ruler, and this is actually an extremely robust standard ruler because it's very hard to mimic this feature in the distribution of galaxies with spurious signal, systematics, foregrounds, anything. This is actually really easy to tease out, and it gives us a really, really clean measurement, which I'll talk to you later. Okay. So with the goal here, we built this to study dark energy. And I would say I started doing dark energy science in 2004. And I would say between 2004 and 2024, I was convinced we would find nothing. So I spent 20 years of my life doing these types of measurements, either with supernova or with BAO. And the reason I thought we'd find nothing is, one, I thought that dark energy was a cosmological constant, that we already had the model figured out. And two, it's really, really hard to tease out the difference from the cosmological constant. This gives you an idea of exactly how hard it is. Here is, if I take the equation of state, so I allow it to evolve with time in a different way than the cosmological constant that we have as a standard model, here's how much it leads to differences in the distance versus redshift relationship as a function of z. If we're talking about measuring differences at the 1 or 2% level. Okay. It's really, really hard to make that measurement. And to give you a kind of a feeling, this range from the blue to the red, that's actually our 3 sigma error bar. So what I'm showing here, that plus or minus 2.5% fluctuation is 3 sigma for us. So it's really hard to measure. Okay. A more common parameterization is more general, is one that not only is the equation state different from that for the cosmological constant, but it varies with time. So it's now 2 parameters, one parameter that anchors it to redshift 0, where we are today, and one parameter that basically allows it to evolve with time. That's the WA. And you can see it's still equally hard to measure. Here I've held W not fixed, and I'm turning this knob in WA by plus or minus 0.4, and I'm still seeing like 2% effects. And these are the 2 measurements I'm making with my BAO, the angular diameter distance and H of Z, the Hubble parameter. Okay, so really hard to make. So I didn't believe we could do it. I didn't believe there would be anything but lambda, but we went ahead anyway.
Kyle, but there is this code show that there is some sweet spot of redshift that you can.
Oh,
Okay.
yes.
When is that redshift 0? What did that mean?
So, I unfortunately I don't have that many Hubble diagrams in here. We're going to do much better in 2 weeks, okay? But the sweet spot really is redshift 0 for both of these. You get some variation here, but it's very hard to measure the co-moving angular diameter distance at redshift beyond 0. BAOs, because the precision I can make the BAO measurement depends on how much volume I have, because that tells me how many pairs there are. I don't have as much volume in this area as I do here. The sweet spot for BAO is basically here to here, okay, for our measurements. And that's going to kind of play into this story a little bit. So we do extremely well, okay? It's hard, okay? So we've been at it. When I joined my faculty position, I joined the Longitudinal Sky Survey. That was in 2009. And we spent 4 generations of that project. I was in the last 2, but 4 generations of that project building up this technique along with other science. How do I make BAO measurements? How do I do my redshift surveys, blah, blah, blah. Here's the Hubble diagram that came out of that 20-year project. This is the Hubble diagram from about 4 million redshifts. Okay. And you can see we've normalized it to the preferred model from Planck. So we've just taken the predicted expansion history from Planck, divided that out, and anything that differs from one is tension with Planck. And you can see we're able to make these measurements in that survey at the sub-percent level, or about the percent level. Okay? And we also covered that wide redshift range, right, from all the way out to redshift 2. But you notice what I was saying before, right, we're not as sensitive at the lowest redshift. The error bar here is 2 or 3%. And actually at 2%, you're like barely measuring feature. Okay, but that's real data. Those are our correlation functions, and you can clearly see the peak at 100 on each megaparsec in each of those.
And grad students, Ashley Ross, Illinois grad student.
Yes, I've known Ashley a long time. I knew that and I forgot that, but it's a true story.
Sure.
He's still with us. He's now in Columbus. So BAO was really the primary technique. That's really the cleanest thing to measure in the clustering of galaxies. But it's not the only thing we measure. There's actually a ton of stuff that comes out of it. Another key thing that comes out of it is called redshift space distortions. And redshift space distortions are shown here now a 2D correlation function. So this is still excess probability above random, but it's now perpendicular line of sight and parallel line of sight, so it's in 2D. And you see it's not spherically symmetric. It's squashed. And that squashing is because your redshifts capture not only the cosmological information, but also the peculiar velocities. So you can literally track the statistical infall of galaxies into gravitational wells over all of cosmic time. And that rate of infall is a function of the growth rate of structure. So we parameterize that with this F sigma 8 parameter. That's a combination of the amplitude of growth, the fluctuations, and the growth rate, okay? So growth of structure carried in here. And not only that, but the whole shape of the power spectrum, not just am I getting these wiggles, this is now in Fourier space instead of configuration space. Those are the wiggles you see in the CMB, right? This shape, this broadband shape, also captures information about the neutrino mass. It captures information about omega matter. There's a lot of other physics in there. It also captures information like light relic particles, their contribution. And we're trying to tease it all out. The only thing I'm going to talk about today is the growth of structure that comes from this. I'm only going to hit on a few cases. So this F sigma 8, I'm going to fold those into in cosmological interpretations. Okay. So we use this technique. I showed you a Hubble diagram from Sloan. That was 10 years of work for me and 20 years of work for everyone else. And I'm going to show this figure for a reason. And it's really partly about the robustness of the technique. So after those 20 years, this was our constraints from the cosmological model. W naught WA are those two parameters that describe the equation state and allow it to vary with time. And if you look at the W naught WA plane right here, when I combine all the information I had at the end of 2020, which was supernova, BAO, and CMB, Planck, we see what's here in the gray, okay? And notice that it has a preference to sit in this bottom right-hand quadrant, but it's not statistically meaningful. And we didn't think anything of it. We swept it under the rug. It had a slight preference, but it was at the 2-point-something sigma level. And all we talked about in our legacy experiment was how precisely we could measure these parameters. We didn't talk about the central values at all. Okay? I would say 2 sigma is kind of in the regime of, mundane.
What year is this?
This is 2020.
It's 2020. Sure.
Yeah, so this is the legacy of Sloan.
Mm-hmm.
Okay, now, so that's where we were in 2020. We start DESI. It actually started we started commissioning it in 2020, just as COVID was hitting. We got we just got enough spectroscopy to make use of the COVID time. We came back up and we were, boom, ready to go when COVID was over. Okay, so it's the same kind of concept. We're studying galaxies, quasars, and line of a forest for our clustering technique. Those are the tracers. We're doing so with the Mayall telescope outside of Tucson at the Kidd Peak. We took it over. We upgraded the telescope so we could instrument a wide field spectrograph. That included changing the optic and some other things. We built our instrument. It's a 5,000 fiber spectrograph. Okay, and everything was optimized for making these BAO measurements, although as I said, a lot of other physics comes out of those clustering measurements as well. The goal was to improve our precision by a factor of 10 on that W naught WA space relative to where we were when when people wrote out the roadmap for dark energy science. And we're really right now, we're the only project in town doing this at the level of precision that we're doing it. We're the only spectroscopic survey working at this precision, and we're the only stage 4 project in cosmology right now. Okay, and lots of other good stuff comes out of it. I care about all of it, and I'm not going to talk about any of it today.
Now I have a question, what are the stages defined?
Yeah, so when the Dark Energy Task Force laid out the roadmap for, studying the physics of dark energy, they had 4 stages. And at the time, it was stage 2, which was basically post-discovery of dark energy, but at the stage where they're just making the first measurements. At that time, only supernova existed. So stage 3 was BOSS and EBOSS. It's like DES supernova, it's Planck. That falls into stage 3. And then stage 4 was kind of like the ultimate end goal. There was the build up to that point where we could measure things at a precision where we thought we might find physics. And I didn't believe we'd find physics. It's a long goal. The whole idea was to get a factor of 10. And that's in a 2-parameter space. So it's only a factor of 3 on each of them individually. It's a hard game. It took 20 years.
So this station refer to different programs, right? Supernovae are in stage 4.
There will be supernova in stage 4. So it's more about precision that's allowed. So the primary drivers for each stage are really, weak lensing can be argued to be in there, but I think in my view, supernova and BAO and CMB are the real key things. Okay, so we just get better and better and better at each of those. Yep.
Is there gonna be a stage 5?
We're trying for it. So yes, I've been talking about that since 2016, and the goal is not late time physics anymore. It's early universe physics. And it's basically, what's my show on the next slide? Yeah, so here's my slide of the redshift range for DESI. The real our real sensitivity is in this area between redshift 0 and 1.5. The future is between redshift 2 and 4. That's stage 5. And the goal there is to get it, kind of try to limit the amount of processing of the matter density field from gravitational collapse and all the stuff we don't like, and really try to tease out the initial conditions. But that's basically, we have to do something at the level of DESI, the same volume, same number of galaxies, but at redshift 2 to 4. It's really hard. So you need a much bigger facility than what we have. Yeah.
Initial conditions, the CMB provides a set, right?
But only in 2D. We could beat the CMB in 3D because we have many, many, many more modes. So right now, it's complicated. We're kind of close to being competitive with what we have, but we can do much better. But what I'm saying is a lot of caveats. Okay, for the early universe physics is really hard for us. In some ways, it's easier for the CMB because they're totally linear. But we have a lot more modes, so that's a balance. Okay, so the redshift range is as shown here. This high redshift range I'll talk about in a second. Those aren't direct tracer, but that's illuminating the intervening intergalactic medium through the Lyman alpha forest transition. Everything else in this area is looking at direct tracers, one galaxy, one spot on this figure. Okay, and there's about 40 million redshifts we're expecting over 5 years. We also have a large survey of Milky Way stars, and we're gonna do some cool stuff there, and I'll suggest speakers maybe in a year or 2 for your department. Okay. So lots of reasons DESI is more powerful than Sloan. I like this video, even though it's not really relevant. I just think it's cool. So this is how we used to do things in BOSS. For every plate that went on the sky, we had a human being plugging in the fibers and trying not to get carpal tunnel. I would take something like 2 hours to do this, maybe longer. This person doing it, her name was Diana Holder. She was trained as a dental hygienist, so she was an expert of working in those small spaces and could do that much quicker without breaking any fibers. Of course, now
Escape.
okay. So now we phased out the humans and we have robots moving those fibers. And then now we can actually do it in real time. So we do the fiber assignment field by field rather than having to plan out 9 in the afternoon. And each of these robots covers an area of just a few millimeters. They're, smaller than my finger, of course. There's only 2 motors on each. And they can position a fiber optic, which is about 105 microns in diameter, to 10 microns precision. So your human hair is something like 100 microns. So you can do it something like a precision of 1/10 of human hair. We have cameras that image them and determine their exact location. It takes 1 minute to get them into place. When I move to a new field, I have all my targets I want to observe. It takes 1 minute to put these 5,000 fibers on those 5,000 galaxies. Okay, so that going from 1,000 fibers to 5,000 gives us a factor of 5 more power for DESI compared to Sloan. We also get a factor of 2 or more by going from a 2.5 meter telescope to a 4-meter telescope. And then we have spectrographs that look a lot like the Sloan spectrographs, but with slightly higher spectral resolution. But very similar wavelength coverage and a lot of the actual techniques we put into place in Sloan.
I'm a little confused what I'm seeing in this video.
Yeah. So each of these is a robot, and it's moving the fiber, which is held in purple, to the position that will align it with the galaxies. The telescope focuses the light down that fiber, down the pipe.
So are we looking from the front of the focal plane?
You're looking,
The telescope?
good question. Okay, so the primary mirror is down here. This is all held up at prime focus. And we're looking as if we were at the location of the primary mirror, looking up at the focus position. Okay.
And how do they move? How do they put this position?
And there's 2 motors. It's of this design. So one motor moves in this direction, one moves in this direction. So those are degrees of motion, or degrees of freedom.
And where are the actual CCDs down?
All the spectrographs are down here. That's in a room that's temperature controlled. One of the problems we had in Sloan is that changes in temperature, changes in the position of the telescope, changes in humidity, they all change the wavelength solution, and they change the flux, even like the flux calibration. So effectively, we put everything on a bench and run the fibers from 40 meters from up at the top down into this temperature control room. And that makes a huge difference in our ability to do our calibration. And Sloan, that was on the back of the telescope. So as the telescope slewed around, the gravity vector changed and all the optics kind of shuffle around. It's an awful situation. Okay, we did this in VOS and EVOS. What we did in DESI, once we had a year of data, which I actually don't, I may show a footprint, but let's say we've already moved on a year of data. I've cut out all the slides to save time. We used the same techniques when we started from scratch on everything, and we revisited every step and diagnosed it and dissected it to make sure we understood the robustness of the measurement, systematic errors, tuning the knobs on the analysis pipeline. So not only at this time, after 1 year of data, we took 10 years to get 4 million objects. We took 1 year to get 15 million with DESI. Okay, so we already outnumbered Sloan by a large factor. We also did this blinding, which we never did in the past. We just had everyone do a different technique. They all got their own data sample and they made their own BAO measurement, but they looked at the results, they looked at it compared to LCDM, so on and so forth. we actually intentionally corrupted the position of all the galaxies, so no one knew what the truth would be. We corrupted it in all kinds of ways, kind of crazy. But the idea was to mitigate confirmation bias. So no one could actually try to tune their measurement to the location of lambda CDM's prediction. Okay. And this just tells us a little about what the blinding was. Really, we did it in peculiar velocities. We did it in primordial non-Gaussianity. We did it in VO. We changed the distance redshift relationship. We did all this stuff without knowing what we were doing. And we hid it from ourselves every which way. We did all the testing with the blinded data. And effectively, we found almost nothing in terms of systematic errors. All the data splits, theory tests, cosmology tests, very, very small amounts of systematic error, super robust. Observational effects made no difference. Reconstruction made no difference. Choice of covariance matrix made no difference. At the end of the day, the full level of systematic errors, when we take into things where we actually, I think these are overestimated, okay? But it's at the level of 0.25% is that we're finding in terms of systematic errors. We treat them as if they're random errors on top of our measurement errors on each of these different redshift intervals, okay? I think this is too much. I think it's probably half this in truth, okay? Okay, the effect when we made our independent measurements is that conservative estimate of our systematic error budget took what was the original statistic error and increased it by 5%. So that's a degree that tells you like what robustness, how well we trust the analysis. Okay. Now, we do that, and here's what the results look like in a chi-squared sense. Now, values of 1 mean that you're getting the peak position that's predicted from Planck's model for lambda CDM. And this is the chi-squared surface for each of our tracers that we do. And now we break up the sky into those redshift intervals that kind of showed like the earlier figure I showed when I showed the pi slice of the universe. So in the lowest redshift, we're measuring at 4 sigma. The next redshift, 6 sigma, 7 sigma, 9 sigma, 3, 7, and 4 sigma. Okay, and this is not yet with the laminal forest. So those are the different redshift measurements we made of the BAO peak. The aggregate precision, when I add them all together and take their uncertainties, we are measuring the distance at 0.5%. So that's the best we can do, basically. We're measuring distances at 0.5% precision. After 2 decades of Sloan, we're measuring things at 0.64%. So we've already in 1 year of DESI superseded that effort. Now, I say we do galaxies, we also do the laminal forest, all the same idea. The only trick here is instead of using direct tracers, you're using these absorption lines that's observed as the background quasar. That light mixes with the intervening neutral hydrogen, it gets absorbed. So you trace out the three-dimensional structure of neutral hydrogen, and just play the same game of counting pairs. But now you're doing pairs of hydrogen instead of galaxies. Okay. The laminal forest data, when I did it in Sloan, it looked like this in the gray. When I do it in DESI, I get what's here in the blue. And if I combine the two, I get what's shown in red. And again, that's measurements in both directions that are about the 1% precision. Okay. People have been asking about the data release. Our data we're going to make public from this measurement in 2 weeks at the APS meeting. And this is the footprint. And you can see it varies in the darkness of the circles. That shading tells you how complete it is. We visit each coordinate of the sky 5 times. And places where it's spotty have only been visited once. Places where it's filled in and dark, they've been visited 5 times. Okay. But you can see we have a lot of area, but it's only 1 year out of 5, so it's only something like 20% of our final sample. Okay.
Why does it even DR1 not, why does that not blow SDSS out of the water?
Okay, so back before, SDSS was giving me points. SDSS was really amazing. after 20 years or 10 years. I was at 0.64% with my galaxy tracers.
Yeah.
I got to 0.52% in 1 year. I'm seeing a comparable gain in alignment alpha forest. It's hard to compete. Even if you have 10 times faster instrument, you have 1/10 the time. So it's better,
Yeah.
but it doesn't blow it out of the water yet.
And isn't this measurement where the higher spectral resolution really, where you really win most?
So we actually bid the pixels, so resolution doesn't matter, it's about signal noise.
Okay.
The resolution matters more actually at the longer wavelengths, it's about sky subtraction
Gotcha.
and identifying the O2 doublet. It's not about resolving the forest.
Gotcha.
Can I quickly ask a quick, slightly technical question on the correlation stuff? You've probably done this also as a function of redshift bins, and you're expecting probably more correlation if you're only considering lower redshifts, and then it should drop off as slow as efficiency drops off. Is that what you see? Like, is that 10% number overall correlation?
Okay. Okay. This right here you're talking about?
Yep.
Okay.
Is your-
That's a very technical question. It's higher for galaxies than for alignment alpha forest. And the reason is for the galaxies, we're pretty much in the cosmic variance limited regime. Here, we're barely sampling the sky, so it's all about shot noise. So the more I get per coordinate, the quicker I go down. So the correlation is actually pretty low between them. But it's all about the balance of shot noise versus volume.
Sorry, is this comparing, say, the redshift that you measure per given galaxy to that measured by SDSR?
This is actually literally calculating the measurement of the BEO feature. Okay, so it's literally what's the correlation coefficient between the blue and the gray? And it's only 10%. So it's almost an independent sample. That's not true. It's not, actually, I'd say it's less true at low redshifts.
And
I think it's 30%, 25% at low redshifts.
and with Sloan, was there a larger, the balance of systematic and statistical was different?
We assigned no systematic errors in Sloan. I believe we can get away with assigning no systematic errors here, almost. I think the only thing that's really true is we don't know some of the cosmology that we use for reconstruction. My opinion is probably all that really matters. We don't know some things about how galaxies are sitting in halos and some about the growth history.
So when you say that this 10% means it's almost that these two are independent, does that mean roughly the same thing as the measurements being inconsistent, or am I misunderstanding?
Okay. So the question is, does it mean they're inconsistent or not? This is the blue DESI, this is the gray Sloan. Their 1 sigma contours overlap. So if I take two measurements, they're completely random and uncorrelated with each other. If they overlap at 1 sigma, that means they're consistent with each other.
Okay.
If they're highly correlated, if the correlation coefficient was 100%, and they look like this, there'd be a problem.
Alright.
Okay? It's correlated, they should give you this, it should give you the same result. That might come up in conversation later. We had a discussion earlier this afternoon about this. It's not about DESI. Okay, so now let's talk about the cosmology and what this all means. Okay, so those are our measurements. We have RSD measurements, we have BAO measurements. The BAO measurements, I put them on the Hubble diagram. I do it for each specific to the tracer. This is the lowest redshift. What I'm going to show you on the left is this is like a isotropic measurement. So this is going to be the BAO distance relative to the Planck. This is going to be the cosmology constraints from that individual bin in the parameters most suited for the Hubble diagram in a LCDM model. The two parameters are omega matter and what's effectively the Hubble constant, but I'm going to do it with the Hubble constant where I don't know the exact scale of the BO features. That's why there's this R sub D in there. Okay. So here's BGS. Here's the next redshift interval. Two more measurements in the Hubble diagram, measurements in the red. Here's our next interval. This is combining luminous red galaxies and emission line galaxies at the next redshift. That's about redshift 1. I go to higher redshift. This is my highest redshift galaxy sample. This is emission line galaxies. That's something like a redshift 1.3. Beautiful measurements of the feature. Here's my quasar sample. Here's my Lyman alpha forest sample. Okay. I combine all of them. And I get, without any other probe, I get about a 5% constraint on omega matter and about a 1% constraint on the Hubble constant. Okay. And you can also see that they're all consistent with each other. Within lambda CDM, they all overlap. These are all independent measurements. There's no correlation between these databases. The quasars have a tiny correlation between other things, but almost not. And they're complementary. But you can see that's how the rotation kind of changes. They have slightly different redshift intervals.
I'm a little confused why the quasars have a lower mean redshift than the Lyman alpha. I mean, quasars have the backlight.
Okay, so quasars are the backlight above redshift 2. But we actually get quasars between redshift 0.8 and 3 or something like that, 4. And we can't backlight Lyman alpha below redshift 2 because it's not in our wavelength coverage. So below redshift 2, we use them as direct tracers.
Okay, so different samples of quasars.
Exactly. That's right. It is an independent, that's exactly right, independent sample of quasars. And I'm glossing and over things. There's actually quasars in Lyman alpha 2. We cross-correlate the quasars with the Lyman alpha forest, but I'm not talking about that. It actually makes a big difference and it helps, but I don't think it's important today. Okay, so I combine those measurements in omega matter and H naught. This is what DESI looks like. If I compare that to what we did in Sloan, super consistent. Correlation coefficient's pretty low, but 0.25% or 0.25. Totally consistent in omega matter and H naught. I compare them to Planck with a lambda CDM. And here's Planck, very narrow but highly degenerate, consistent. Okay. I can combine these, and my omega matter, combining the CMB and the DESIs, 100% precision. Now, a lot of talk about the Hubble tension. You can derive the Hubble constant from BAO data without any CMB. All you need is something to give you the baryon density. So we can use Big Bang nucleosynthesis. And we're basically able to measure, we extract basically treat the CMB as another BAO measurement. And that's the only CMB information we use. We don't use the other stuff about omega matter and omega baryon. We can measure at 1% precision, independent of CMB. Okay. You can see what the values are compared to what we did in Sloan, totally consistent as we expect. You can also see the values compared to CMB without BAO. We see a little tension, and actually there's also that tension in omega matter in the opposite direction. Kind of come back to that, but it's really, I would say, pretty damn consistent between BAO and CMB. And then you show the low redshift probes, the direct measurements. Okay. If I look at the Shoes collaboration, this is the source of a lot of this excitement about the Hubble tension. I prefer to call it drag scale tension because that's actually the real physics. So the R sub D that determines the scale of the BAO feature, right? That's theory behind that. So Shoes and BAO give you different results, and they're both correct. It means that we've got the physics behind R sub D correct. And that means we found something in the early universe that's tweaking it. So here's Shoes. This is like a 4 or 5 sigma tension with BAO and with CMB if you treat it in isolation. Or you can ask the group in Chicago, not very far from here, and they don't find that tension. They have a different probe for low redshifts, that distance ladder, that low redshift distance ladder. Okay. I don't know what's true. I have complete confidence in this stuff. I don't see any reason that could be wrong.
Did your hand go over the orange stuff?
It went over the orange too. Yeah, actually.
And the gravitational waves is still pretty broad, right? It does your thing.
Really, we only have, there was only one event where we have a redshift. And I think the error bar, I forget what the error bars are, 6, 10%, something like that. I don't know exactly what the number is. Okay, so so far things look good. If I look at the simplest form of dark energy, where it's not the cosmological constant, I can allow it to not be equal to -1, but the data don't want that. The data still want lambda CDM as my primary model. And I can see that for all these different data combinations. Here's my DESI in blue, here's my CMB in purple. This is now W on the y-axis, that's my dark energy term. And these three dashed contours, boom, 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 those are three different supernova samples, okay, from three different groups. There is covariance between them. They have the same low redshift supernova in common. Two of them have the same high redshift supernova in common. But I'm going to refer to these several times. One is called Pantheon Plus. One's Union 3. One's DES Year 5. Okay. But so far, everything jives. Looks good. Any questions so far? So lambda CM looks like the correct answer. But what I'm going to do is actually keep with lambda CM. Sorry, I forgot to put this. This is another good slide. So I can also look at the growth of structure with those sigma 8 measurements. Okay. This is exactly the same thing as what I showed you before, but instead of omega matter and H naught, it's now omega matter at sigma 8. Sigma 8, you've heard a lot from the lensing community
我觉得
about
这个肯定
tensions.
是要重新看的，最好能把 slide 给弄过来。
Oh, great. It happens all the time. So sigma 8 has been low from a lot of lensing surveys or with varying degrees of statistical confidence. Our measurements in all the individual tracers in all the different redshift bins, they have very complementary results, just like the BAO, they overlap. And combined, they get a pretty precise measurement of sigma 8, something like 3.5% precision. And we're being very conservative. We're not taking the information from the shape of the CMB power spectrum. We're have a really loose prior on the spectral index. If I tighten that spectral index up to what we actually know from the CMB, this number goes, the precision goes down, and this gets a little bit closer to the CMB predicted value. So there's nothing interesting there. Sigma 8 looks to be spot on predictions. Okay. This is a view of that. Sometimes, because the lensing community measures a combination of omega matter and sigma 8, they use this S8 term instead, which is a little bit harder to understand because it's a combination. But you can see the CMB predictions up here in orange, our measurements in blue with this conservative prior on the spectral tilt. Here's what we did in Sloan. Looks a lot like DESI. Yet again, we revisit everything. We do the pipeline, new data, do everything from scratch. We actually have a totally different formalism. We have a different theory behind it. We got the same result. Okay. And then so the lensing, it's, you know, your matter of taste. Are these discrepant or not? The lensing community has spent a lot of time typing this up, but we don't see it.
These are 1 sigma error bars,
These are 1 sigma error bars.
so it doesn't look inconsistent.
Yeah. There's a lot of discussion about lensing is low. I don't disagree with you. And I mean, we're totally linear physics here, and we don't see it. Okay. Now, what we can then do, going beyond lambda CDM and going beyond the simple form of W, we can go to this more flexible form for the equation of state that varies with time. Okay, these are some of those curves I showed before with these 2 free parameters. And because the DESI data, this is what you asked about the redshift range, they don't have that redshift range down to redshift 0. So it's very hard to differentiate the lambda CDM prediction, which is where these two cross, okay, and non-lambda CDM, which is anywhere else in this parameter space. Okay, DESI alone, very hard to interpret. We're something like 1 to 2 sigma consistent, depending on what data sample we're talking about. It's not very interesting yet. Okay. If I add in the CMB, that gives me a much tighter constraint on my matter density and my coupling of my time evolving omega matter versus my matter at the time of the CMB. Now I'm starting to see something. And look, this curve now in purple looks exactly like the curve I showed you from our 20 years of Sloan. Same quadrant, the same tilt, the same area, the same level of tension. It's moderate. It's a 2.5 sigma tension. So what this says is that my model for dark energy that's not lambda is preferred at that level over lambda CDM. Okay, so there's 2.5 sigma preference. Okay. But I'm starting to see it without supernova, just CMB and DESI. Okay. Now I can add in those supernova data samples. And I added each of them. I never combine them because they have so much covariance that's not well characterized. So I have 3 independent measurements. Our data plus CMB plus supernova sample 1, plus supernova sample 2, plus supernova sample 3. These are all 2 sigma contours. And the preference varies a lot between them. So this is the sample here, this Pantheon Plus, that was the closest to the supernova sample I showed you from the Sloan. It's largely in common, the same group. The supernova are largely in common. They've made some tweaks, but very similar. The Planck is the same. The only thing that's changed, basically, the biggest change is DESI versus Sloan, but it looks just like that figure I showed you before, and that's 2.5 sigma tension. So that particular supernova sample doesn't even increase the tension with lambda CDM. On the other extreme, I put in the DES sample, and it's now almost 4 sigma tension. So that gets you into the realm of, of real legitimate tensions, whereas 5 sigma is brand new discovery. Okay. I'm sorry.
Maybe we're gonna talk about this. I suppose we should be glad that it's not the left.
Yes. I'm not gonna talk about that. That's that's a good point. I like that it's the bottom right hand column.
What are we ruling out now? Are we able to rule anything out of this?
So
Besides lambda, well, potentially lambda.
So the way I look at this is very agnostic. I'll show you some more information. I think there's 3 to 4 sigma tensions with lambda CDM, generally speaking. I don't know if it's dark energy or not, but the Hubble diagram or the distance redshift relation we measure is not what you would expect from lambda CDM. I don't know what the source of it is. You can imagine something changing, some other behavior changing it. You can also even imagine the BAO standard ruler is not being calibrated correctly. It's being distorted from new physics. Something else could be happening, but it's at the 3 to 4 sigma level. But it really depends on supernova sample. Like if I saw this is what I was expecting when these 2 results came out like as we were writing the paper. And then we got into arguments whether or not we even included them. If we had just done this, no one would have given it down. But 4 sigma, and I can tell you, we have 3 years of data. It's coming out in 2 weeks. What do you think that number's going to do? It's going to be higher or lower? DESI is always DESI. It gets better and better and better. So that precision is going to get tighter and tighter and still be consistent. So you can what direction it's going to go in. It's going to get more and more tense. So now we're going to be in the 4+ sigma regime.
And DESI by itself without the supernovae? And after the 3-year data?
This is smart. We'll show some nice curves that demonstrate this, but the lambda CDM curve is highly degenerate with the W.WA CDM curve in the redshift range of DESI. It's very hard to disentangle the 2 models. And that's just because that redshift 0 is so important.
So if this 4 sigma deviation is true, does that also solve the Hubble tension problem?
No, it pushes H naught in the wrong direction. It pushes it lower.
Okay. So still have a problem.
Yeah.
Oh, Brian has a question.
Yes.
Brian, do you want to go?
Yeah, sure. I mean, Kyle, you and I discussed this, but just to sort of do a little foot stomping about this. I mean, it's a big deal because this would be, the death of lambda, and something more interesting replaces, or more complicated anyway, replaces it. And the WA you get is negative, so that means the amount of dark energy is sort of decreasing over time, right?
Yeah. So as I go to this was you asked about comforting. So as I go towards redshift 0, whatever used to be dark energy is starting to evolve to look a lot more like matter. So the equation state is evolving from W equals -1 at high redshift towards 0, which is what the equation state would be for matter. That would be for pressureless dark matter.
So some kind of decaying dark energy.
Yeah, we call it thawing dark energy.
Oh.
So it all depends on what you want to read into this as well. Like if I take this W naught, I mean, we could talk about, in DESI, we talk about this for hours on it. If I take this really literally, these values of W8 actually push me to cross, give me a phantom crossing, which violates the null energy condition. And it actually, it's not 5 sigma level, but it's favored over no null energy crossing, or no null energy condition. So it's violating that with some preference. Well, we'll show that figure in the year 3 result. We do a much better job demonstrating where this information is coming from in year 3. So in 2 weeks, we'll show this at APS. And we spent a lot of time showing where this information is. And like I said, everything's going to go up. And what I'm showing here is actually, I mean, I glossed over it, but there's 2 curves, dashed and solid. That's just with and without the RSD measurements. So RSD helps at the 20% level. It shrinks these contours by that much in area, but it doesn't, it's weaker. Most of this information is coming from BAO.
So as you point out, the supernova samples are correlated and they have the same low redshift sample. If you exclude the low redshift sample, which you need because it's 0,
Yeah.
How much worse does it get? And do you still see the tension if you only?
Yeah, so if I exclude the low redshift sample, I'm going to get something that looks like this. So the nice thing about the supernova, if I just match, right, the part of the reason there's tension between supernova and BAO and lambda CDM is because they have different redshift ranges. So if I just cut the redshift ranges to the same lambda CDM model out, and that's true for all the supernova samples, I believe. And then I cut out the only tension I could find on lambda CDM is when I compare that now joint Hubble diagram to CMB. So it's going to look a lot like this. I don't know what the precision, what the tension is exactly, but I can't imagine it's much more than 2.6 sigma. I mean, Pantheon Plus, I think, will basically do that. Because Pantheon Plus has a very Planck looking result.
So suppose you have a supernova sample at a redshift greater than 3 without help situation.
It could ask questions about like the phantom crossing, things like that. For me, the most exciting supernova sample is between redshift 0 and 0.6. Like super, super robust, super clean, no selection effects, just perfect beyond perfect. That's what I would like to see. It's hard.
It's an experiment called the Rubin Observatory that I believe.
Yeah, amazing. Maybe it's spectroscopic redshifts. Maybe. So I don't know. You know, it's the supernova do play a major role, and the CMB plays a major role, and the BAO play a major role. They're all super important in this. Okay. I mean, BAO is doing things at 0.5% precision. Okay. Okay. So we kind of step back and we look at what's going on back in this tension, the omega matter. I think a really interesting thing is, you know, okay, W not WA are the better fit to the data, but they actually also resolve some problems in the data. If I fix myself to lambda CDM, this is what I was referring to a second ago, and I just treat each sample independently, the supernova, the BAO, right? This is the omega matter likelihoods, and those 5 measurements, 3 supernova plus BAO plus CMB, each individually, so 5. They are not consistent, okay? And that's because each of them is sampling a different redshift range. So if lambda CDM is the wrong model, you're going to get a different lambda CDM result if you sample it in different epochs. And that would be consistent with what we're seeing here. You can also ask about the lensing and the low structure growth. This demonstrates 2 things. One, that if I work with a lambda CDM, I get the black contours. So I get a sigma 8 that's consistent with the CMB prediction. If I add in the supernova and I open my cosmology background, so I now have a time evolving equation of state, omega sigma 8 doesn't actually change very much. So we're really robust. Our growth measurements are really robust to the structure growth, and changing the model doesn't change that story. Okay. The one thing that kind of does change is the whole curve shifts to the right, which is what's happening here is it's just merging these all up. So when I go to my flexible model, it gives me an omega matter that resolves the tension that I otherwise would see omega matter here. Okay. One other source of tension, okay? Another problem in lambda CDM is the neutrino mass. So neutrino mass, I'm not gonna talk about the physics behind it, but it's there, it affects geometry, it affects the expansion rate, it affects the growth of structure, it affects the shape of the power spectrum, it shows up in a lot of ways. And if I combine DESI in green, let's say, with Planck, and I force myself to have a lambda CDM model, I can tell you I get a really, really tight 95% upper bound of the neutrino mass. I can tell you it's less than 71 millielectron volts at 95% confidence. That's a key measurable in particle physics. Particle physics experiments can't measure the absolute mass, but they can measure the relative masses. And if you look at the relative masses and set the lowest masses to 0, the lowest possible mass is 60 millielectron volts. So we're basically at that, right? If you look at this in this cartoonish view, right, we're at that level. We're already telling you it's the minimum mass scenario in the normal hierarchy for neutrinos. So we've solved the problem that like Dune is trying to do. Okay. But notice that these contours look very funny, extremely non-Gaussian. Everything is kind of globbing up on the prior, the m is greater than 0. If I open up the model to allow a time evolving equation state, my cartoon view, I soften the error bars to 200 millielectron volts. So I soften them by a factor of 3. But now what I see is a posterior that's Gaussian and it peaks at a positive physical value. So really what I'm seeing here is pathological behavior where the model's trying to use the neutrino mass to accommodate those tensions in the redshift history, right? In the distance redshift relationship. Okay. So I can soften that and I can resolve that problem and get a very physically well motivated neutrino mass without changing the error bars very much. It looks like it's inflated, but the actual width of the Gaussian is not that different by opening up to this flexible model. So I've now taken this pathological behavior and fixed it.
Except for Pantheon.
Yeah, Pantheon still looks better. This still looks more Gaussian. That's peaking. I mean, this peak in the last one is like negative 120 millielectron volts or something like that, if I really extrapolate it. I'm sorry.
So, the mention, is it electron neutrino specifically, or it?
Okay, so this is the mass eigenstates, and this is the sum of the M1, M2, and M3 eigenstates. Okay, so that's actually what we're sensitive to in cosmology. Okay, so I think that's the end of my story. What I want to tell you, I've already said it, I'll say it again. This is all year 1. We're actually almost finished our 4th year of observation. Because we now have the tools and the collaboration, all the effort, we cranked out our year 3 analysis very quickly. We've been sitting on it since, I don't know, November maybe. So I know what those results are. It looks great. And it's coming soon. You will see it, I think, on March 18th. We're presenting those results at the APS meeting. My colleague, I used to be the spokesperson for DESI. My colleague, who is the co-spokesperson, she's giving a plenary, not on the new results, but on the old results, and in prepping up for that special session. So if you're at APS, check out the special session, and we'll show you what's new with year 3. Okay. Otherwise, my summary is, I think it's an important message that we're able to measure the Hubble constant at 1% precision without the CMB that's often lost. It's the same physics, but different probes. DESI alone looks consistent with lambda CDM, but there's a lot of pathological behaviors we see when we look at it compared to other data samples. Matter density, neutrino mass, okay? When I start adding in those other probes, there's a tension with that lambda CDM model ranging in the 2.5 to 4 sigma range. It depends on what's your choice and what's your favorite supernova sample. Okay, the supernova are really key to this, and we really hope that the community can kind of figure out why these measurements are different from each other. Otherwise, keep an eye out. Not only are we going to show our BAO measurements in March, we're also going to release our year 1 data sample, all the catalogs. all the redshifts, there's gonna be something like 14 million redshifts, so larger than any spectroscopic sample in existence. We'll be releasing that in March as well. So thanks, everyone.
So, you focused on the importance of supernova and basically written like the introduction for future NSF proposals, for me. I'm nervous as to why you think this is purely a sample choice effect, because many of the supernovae there are common and numbers that are different.
Maybe I misspoke. I should say supernova measurement. So I shouldn't say, maybe I should say choice of supernova measurement. I agree. My read on it is if you're an outsider, you see two groups, they give them the same supernova sample, and their disagreement with each other characterizes the limits of what you can do in supernova cosmology, if they're both taking their analysis seriously. That's my view. And group number 1 is 2.4 sigma, group number 2 actually is 3.5 sigma. So they differ at the 1 sigma level when combined with all these, with CMB and BAO, it's a huge difference. And those samples are like almost 100% covariant.
Yes.
So that's my read on it. It's all about, I mean, to me, I'm worried about selection effects, how you characterize incompleteness as a function of magnitude, blah, 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 blah. And I don't know which one is right. One is my old group, but I'm still being agnostic.
So from your Hubble tension plot, I'm kind of thinking, I don't believe shoes anymore. But internally, like between these different supernova groups, are they in tension with each other or just with CMB?
So these three with each other are in tension. For example, one way of looking at that is in this figure. So orange is Pantheon plus, green is Union 3. That's almost identically the same. They're like 100% covariant with each other. Okay, it's almost the same supernova sample. So that's the degree of tension with each other. So they should line up perfectly. If you're limited on the sample, or it was problems with the sample, you would see no difference. So this is the difference in analysis. The orange and the green.
So
It's
maybe,
at the 10% level.
okay, so if shoes says 72 or 73, that could be plus or minus 3.5, something.
Okay, but shoes is doing, this is not using the full distance ladder. This is only using supernova 1A. And it probably isn't even using, I think I can't remember what, we may have capped it by 0.02. I forget what lower bound is. Shoes is a whole nother story because every rung in the ladder can contribute to that. And I don't know about, there's been a lot of back and forth between the shoes and the Chicago group. And there's a lot of selection effects. They bounce around each other and you can cut the sample this way or that way, you get different results. It's, again, I'm totally agnostic on that one. I used to always say, I can't imagine they have the absolute magnitudes calibrated wrong by 10%. That seemed hard to believe. But I don't know. I'm agnostic.
But I mean, the thing that's confusing here is that the DES Wi-Fi analysis methodology is pretty similar to Pantheon Plus, and is in much better agreement with DENC, which has a very different analysis methodology. So yes.
But the covariance between the gray and the orange, green and the orange, the covariance is like 100%.
Yeah.
The gray and the orange, it's tiny. So they share something like half this low redshift sample in common. The gray uses like half the low redshift sample of the orange. I forget exactly how much they cut back. And they have a completely independent high sample. When I say low redshift, I mean below 0.1. Completely independent sample above redshift 0.1, all from the same instrument, all from the same calibration pipeline, blah, blah, blah. I worry, but my history at supernova is old. I left the field 15 years ago, but it's all photometric redshifts. And it's not photometric, it's photometric classification.
Oh, yeah.
And spectroscopic redshifts, but not spectroscopic classification. So I worry that there's confusion about identification of the supernova. Not everyone believes me. I might be completely wrong. I don't know. But it's different. It's a different result.
So there's some type 2s in with the type 9s.
I mean, they simulate the hell out of it. And they will tell you they've got that covered. I don't know, it's not, I didn't work on that project. But you,
Gilbin,
So if you just fit to a single W, what happens? Was that up there somewhere?
this is W as a constant.
And that's including the supernovae?
This is with the supernova, and each supernova sample here is shown. They're fairly consistent in this plane, and everything lines up.
Okay,
This model does not have the flexibility to pick up the tension.
right. So now you had the second parameter and now you see the tension.
Yes.
But, so this parameterization was, I think, mainly calibrated on people with like these freezing models. So is there a third parameter that's gonna be like another 3 sigma consistent?
So we're doing that measurement now. There's a million things out there. I prefer as agnostic as possible. So the argument, what I've done, one thing we're putting in the main cosmology paper that was at my request is a third parameter, but it's just bit. So instead of having an analytic form for W, we say, what is W between redshift 0 and 0.25, 0.25 and 0.5, 0.5 and 1, and 1 and above.
W, not rho.
Just W, exactly. And then so we have 4 free parameters that are uncorrelated with each other, and we treat them each independently. And you actually see evidence for crossing over W equals -1 in that scenario with a new data sample. Which could mean a lot of different things. Crossing should not be allowed. So you shouldn't have some on one side, W, like more positive than W equals -1, and some being more negative than -1. Those two should not both exist in tandem. This W not WA model allows anything, and it's anything goes, right? Unless you put those priors on it. And I don't believe, I believe just letting it go, let the data take you where the data's gonna take you.
Sorry for my questions.
Yeah.
Does not make sense. So I'm a little bit confused. So it seems to me like you convinced me some evidence that it's beyond LCDM is required to account for, neutrino mass and the other tensions. But then you still have the Hubble tension.
Oh, yeah.
And pushing in the wrong direction.
Yep.
So is my understanding correct that basically we don't have a model? Then I cannot reconcile.
Well, yes, we do have a model.
Which model?
The model is, I mean,
Do we have a correct model?
can we turn off record? No, the model